Hello, my name is Ting-Wu, and this is a pre-recorded presentation for the 2021 meeting of the Australian Mathematical Psychology Conference. This work is supervised by Professor Eric Bay from the University of Newcastle. Categorical data analysis is common in many disciplines of research, including psychology. For example, categorizing different types of mental disorders and the potential factors that may have association with the disorders. A popular way to analyze this data is by scoring, to determine a measure of association between those categories. I'm here today with a technique that is able to describe the association between the categories of any contingency table. The most common way of presenting two or more categories of data is by cross-classifying them in contingency tables. This way of representing data has been demonstrated to be a powerful statistical tool since the early 1800s, when the famous statistician Quetelet classified various crimes committed in France against some social factors in contingency tables. This method revealed patterns and behaviors of the crimes and was used to describe and predict future behaviors associated with those crimes, which was an important breakthrough in sociology, criminology, and more importantly, the exploration of categorical data in general. The scoring method requires us to understand the notation used for any given contingency table. Let's suppose we have a dataset from a random sample of size n that involves two categorical variables x with I categories and y with j categories. We can denote the ij cell frequency to be nij and its proportional cell frequency by pij, when we basically take any cell and divide it by n. The sum of proportions on the ith row across the columns we denote p.j. Similarly, the sum of proportions on the jth column across the rows is denoted pi dot. Pearsons chi-squared test of independence is the most commonly used method for analyzing the association of contingency tables. Pearsons' intuition stemmed from Galton's computation of the expected cell frequency. He defined that for a cell categorized such that it is in the ith row in the jth column of the contingency table, the expected cell frequency is ith row total multiplied by jth column total divided by n. It wasn't until Pearson who compared the observed frequency with the expected frequency to determine whether there is a statistical difference between them, which is the popular hypothesis test used in Pearson's chi-squared tests. The null hypothesis states that the proportional cell frequency has no deviation from the independence, and the alternative hypothesis being that there is a deviation from the independence. The testing of deviation from all observed cell frequencies from their expected value under independence is what Pearson has derived and known as the Pearson chi-squared statistic. Let's start off by looking at an example. 140 random subjects were classified into different categories depending on their use of sleeping pills and were surveyed how often they get nightmares in their sleep. The Pearson chi-squared test of independence showed a chi-squared statistics of 78 with 16 degrees of freedom, which resulted in a p-value very close to 0. We know that this means we can conclude there is a statistically significant association between taking sleeping pills and having nightmares. What we can't find out from doing this test is how each category contributes to the association. That is, are there particular categories that dominate the association structure, and are there other categories that play no such role in defining the association? Also, are there categories that play a similar role in defining the association, and how can we determine those categories that make a different type of contribution? This is where scoring is able to help us, and we do this by averaging what is known as profiles. A profile of a contingency table is a row or column relative distribution, which allows us to calculate and compare the underlying distribution for each category. For example, take never category and divide the cells by its column total, which give us the column profile for this category. We can do the same for the rarely category, and now we can easily compare and interpret the relative distributions of these categories, which appear to be quite different from each other. In general, we can do this for any row and column such that the relative distribution can be calculated. A profile can be centered at 0 by subtracting it from the expected value under independence. Then each category's profile is centered at 0. The ecologists Hill use these centered profiles to determine the row scores and the column scores, such that the correlation between row categories and column categories are maximized using the method of reciprocal averaging. An initial value is assigned to either the row score AI or column score BJ. Let's suppose we give the column score an initial value. Then we can update the ith row score using the initial value as the weighted average of the ith centered row profile for all the row categories. Summing them will give us a new set of row scores. They are then used as the weighted average of the centered column profiles, which allows us to update the jth column score for all of the column categories, and then the process repeats. After a number of score updates in an iterative manner, the scores will converge to an optimal solution that maximizes the correlation between the row scores and the column scores. The theoretical root of this method can be attributed to Hartley, or went by the publication name Hirschfeld, in his paper that connects correlation with contingency in 1935. To avoid the potential of there being an infinite number of solutions, and to ensure that there are a set of unique solutions for AI and BJ, we use these Gramscreen orthogonalization constraints. Here under complete independence, the scores are centered around 0 and normalized with variance of 1. We can incorporate correlation parameter that captures the correlation between the row scores and the column scores from the reciprocal averaging algorithm that lies within the interval -1 and 1. Upon normalizing and rearranging, both equations can be simplified to give the same correlation equation. This correlation parameter is in fact the correlation between the row scores and the column scores. The reciprocal averaging algorithm can also be represented in matrix form. The matrix R is a diagonal matrix for the sum of the rows. P is a matrix of proportional cell frequencies. The vector C is the vector of sum of the columns. The matrix C is a diagonal matrix for the sum of the columns. The vector R is the vector for the sum of the rows. The vectors A and B are the row scores and the column scores respectively. We have also done some matrix algebra here so that we can rearrange the reciprocal averaging equation into the format that satisfies eigenvalue equation, where ZZT, ZZ transpose, is an I by I square matrix for the row categories, whose eigenvalues is rho, and its corresponding eigenvectors A tilde. So this problem can be solved using eigendecomposition. We can apply this method to a contingency table of any size. The reciprocal averaging procedure will allow us to find the row scores, column scores, and their correlation as a measure of association between each pairs of categories. Let's consider again Nishizato's data to demonstrate an application. At first, we will need the matrix of proportions P. How we obtain this is by taking every cell and dividing them by the total sample size, n. We need the vector R, which is by taking the sum of each row and dividing them by n. The vector C is summing each column and dividing them by n. Then we initialize a set of row scores with the appropriate vector size. Here I have chosen 1, 2, 3, 4, 5. After we normalize the row scores with Gramscreen orthogonalization, we can apply this set of row scores to find an initial set of column scores in this equation. And then we can work out the correlation between them. Now that we have these initial scores A, B, and the correlation between them, we can update them with the reciprocal averaging algorithm. The algorithm will converge to an optimal value or until the desired accuracy is satisfied. Here the iteration will continue until the correlation of the next iteration obtains an identical result to 6 decimal places. In this example, the accuracy is satisfied on the 4th iteration, so the row scores and the column scores here are the scores that maximizes the association. We can multiply the row scores by -1 and leave the column scores unchanged so that the correlation between them is positive 0.647210. We can see that these row scores suggest that the most significant impact to the association structure are from the categories strongly against and strongly for, as their scores are the furthest away from 0. The scores also show each category is quite different from each other in terms of their profile distribution, except the categories against and neutral are relatively similar. The column scores can be interpreted in a similar way. The scores for never and always are very far from 0, indicating a very strong impact on the association. The profile distribution between the categories sometimes and often are similar, while the other column categories are different. We can also compare the row scores and the column scores. Take the scores for strongly against, for example. It is only very close to never, indicating there is an association, and not to the other column categories. The two categories are both very far from 0, and therefore indicating a very strong association to each other. The categories against and neutral are associated to rarely, while the categories for is more associated with often than sometimes. Finally, strongly for is very strongly associated with always. Despite the discussions made of the theoretical and practical developments dedicated to the method of reciprocal averaging in this talk, there are many other related areas of research and issues that have not been addressed with scoring and categorical data analysis. Data transformation is a typical strategy in data analysis to resolve problems such as over-dispersion. However, no discussion has been made in the literature on the impact of the functional transformations, for example, in exponential, logarithmic, or power transformation to the profiles in the calculation of scores. Furthermore, this discussion was based on reciprocal averaging using arithmetic mean to average the weighted profiles. There is another averaging method called reciprocal medians in the literature, which is a more sensitive technique when outliers are present in the data. Research has not been undertaken for other averaging methods such as geometric mean or harmonic mean. Currently, we are developing a generalization of these averaging techniques, which are all special cases to the Lehman mean. We aim to distinguish the best situations to use each of these averaging techniques. Very little has been discussed about scoring with more than 2 variables. We plan to also develop a generalization to the reciprocal averaging method for multi-way contingency tables. Thank you.